Imagine meeting another version of yourself. Same memories, same face, same life, until one decision changed everything. Now imagine not one copy, but an infinite number of them scattered across reality. The instant you split. A single beam of light is one of the simplest things in physics, yet inside it sits a kind of behavior that does not match anything we experience in everyday life. Imagine a single photon, one particle of light traveling in a straight line. It is not split, it is not duplicated, it is not confused about where to go. It moves forward as one tiny unit of energy, and then it reaches a device called a beam splitter. A beam splitter is just a piece of glass or a thin optical layer that does something very specific. When light hits it, the light is not simply blocked or fully passed through. Instead, it has two possible paths. One path goes straight through the material, and the other path reflects off at an angle. With normal light, like from a lamp, you would say half the light goes one way and half goes the other way. That makes sense because a lamp sends out billions and billions of photons, so splitting them is just sharing them out. But when physics reduces this experiment down to a single photon, everything becomes strange in a way that cannot be explained using normal thinking. A single photon does not break into two smaller photons. It is not like a tiny ball that splits into two pieces. It is always detected as a whole unit at one location. So if it is not splitting physically, then something else must be happening when it reaches the beam splitter. Experiments show that when a single photon hits the beam splitter, it behaves as if it goes through both paths at the same time. Not in a metaphorical way, but in a measurable physical way that shows up in interference patterns when the paths are recombined later. The photon acts like it is spread out, even though when you measure it, you only ever find it in one place at the end. This is where quantum physics begins to separate itself from everyday reality. In classical thinking, an object must be in one place or another. It cannot be in two places at once. But in quantum experiments, the math and the measurements show something different. Before the photon is observed, it is described by what physicists call a wave function. This is not a physical wave like water or sound. It is a mathematical description that contains all possible outcomes of the photon's journey. When the photon reaches the beam splitter, the wave function does not pick one path immediately. Instead, it evolves into a combination of both possible paths. One part of the wave function continues along the straight path, and another part follows the reflected path. At this stage, nothing in the experiment forces the photon to choose. The system is still in a state where both outcomes are present in the description of reality. This state is called quantum superposition. It means a system can exist in multiple possible states at the same time, not because we do not know what it is doing, but because nature itself has not resolved it into a single outcome yet. This is not a theory built on guessing. It comes directly from how the equations of quantum mechanics behave when tested in controlled experiments. The key point that makes this so unusual is that the photon does not behave like it is uncertain. Uncertainty would mean we simply do not know which path it took. But quantum experiments show interference effects that only happen if both paths remain active in some form. If the photon had secretly chosen one path early on, the interference would disappear. Instead, the patterns that appear later tell us that both paths stayed part of the system. To see this more clearly, scientists often set up a second beam splitter later in the experiment, bringing the two paths back together. When this happens, the photon can interfere with itself. That means the probability of where it will be detected changes depending on how the two paths overlap. Some outcomes become more likely and others become less likely in a way that depends on the structure of both paths combined. This self-interference is one of the strongest pieces of evidence that something very different is happening at the quantum level. It suggests that the photon is not traveling like a single object with a single route. Instead, it behaves like a spread of possibilities that can interact with itself before any final measurement is made. At the moment of measurement, everything changes. When a detector is placed on one of the paths, the photon is always found in one specific location. It never splits into two detections. It never leaves half of itself behind. The result is always a single, complete event. But the important question is, what happens before that detection occurs? The mathematical description says the system remains in superposition until it interacts with a measuring device. This interaction is not just someone looking at it, it is a physical process where the photon becomes entangled with the environment, meaning its state becomes linked with the state of the detector and surrounding particles. At that point, the system stops behaving like a single combined wave and starts behaving like a set of separate outcomes that no longer affect each other. This is where the idea begins to grow into something much larger. If one photon can exist in a state where multiple outcomes are active before measurement, then the question becomes, what happens when this is scaled up? Because every object in the world is made of particles like photons, electrons, and atoms, and all of these follow the same rules of quantum mechanics at the smallest level. Every interaction between particles has multiple possible outcomes described by quantum laws. An electron can scatter in different directions. A photon can be absorbed or reflected. A radioactive atom can decay at one time or another time. Each of these events has a set of probabilities that evolve according to the same mathematical structure. Now imagine this happening not just once, but constantly in every part of the universe. Every particle interaction creates a branching of possible outcomes at the quantum level. Most of the time, these branches do not remain connected in any meaningful way. They separate extremely fast because of interactions with the environment. Air molecules, light, heat, and surrounding particles all interact with quantum systems, causing a process called decoherence. Decoherence is important because it explains why we do not see quantum superpositions in everyday life. It does not destroy the superposition. Instead, it spreads the information into the environment so widely that the different outcomes no longer interfere with each other. Each outcome becomes isolated from the others in a practical sense, even though they are still part of the full mathematical description. So when the photon at the beam splitter goes into a superposition of two paths, it is not staying in a neat, isolated state. It is immediately interacting with its surroundings. The moment it does, those two paths begin to lose connection with each other. They stop behaving like a single combined system and start behaving like separate, non-communicating outcomes. This leads to a very direct and very physical way of describing what is happening. At the smallest level of reality, every quantum event does not produce just one result. It produces multiple possible results that all continue forward, but without interacting once they separate through decoherence. This is where the idea of every outcome physically occurs, but not in the same branch, comes from. It is not a statement about imagination or belief. It is a description of how the mathematics of quantum mechanics behaves when applied to real experiments like beam splitters, interference setups, and particle detectors. Each outcome exists as part of the full wave function, but once decoherence happens, each one evolves separately. What makes this even more striking is that there is no experiment that shows a clear point where nature chooses one outcome and deletes the others. All observations so far match the idea that the wave function evolves smoothly, and what we call a single observed result is just one part of a much larger structure that is already split into many non-interacting pieces. At this stage, the beam splitter experiment is no longer just about light. It becomes a simple example of a rule that seems to apply everywhere in physics at the quantum level. A single event does not behave like a single path. It behaves like a set of possible paths that all unfold according to the same physical laws until they stop interacting with each other. And if this is what is happening for a single photon, then every system made of particles becomes a collection of these branching events happening at the same time, not as a visible explosion of copies, but as a continuous splitting of outcomes that immediately separate once they interact with the environment. The question that naturally follows from this is not framed in abstract terms, but in physical scale. If every quantum event is producing multiple outcomes that all continue to exist in a separated form, then what does that mean for larger systems that are built entirely from these events, including complex systems like atoms arranged in living structures, and the brain as a physical system made of interacting particles undergoing constant quantum processes. The crisis in classical physics. For more than 200 years, physics seemed almost complete. If you had asked a scientist in the late 1800s whether the universe made sense, the answer would probably have been yes. There were still details to work out, but the big picture looked solid. The rules created by Isaac Newton had survived every major challenge thrown at them. Planets moved exactly as expected. Falling objects followed predictable paths. Cannons, bridges, tides, pendulums, and entire solar systems could be described using mathematical laws that worked with remarkable accuracy. The universe appeared to operate like a giant machine. Every event had a cause. Every cause produced an effect. If you knew the position and speed of every object, then in theory you could calculate what would happen next. Nothing was left to chance. Nothing was uncertain. The future was simply the next chapter of a story already being written by the laws of motion. This idea became known as determinism. Determinism was not just a useful scientific tool. It became the foundation of how physicists understood reality itself. The universe was thought to be completely predictable. Human beings might lack enough information to calculate everything, but nature itself was believed to follow a fixed path from one moment to the next. At first, there seemed to be no reason to doubt it. Then scientists started looking at things that were very, very small. That is where the trouble began. The problem was not that Newton's laws suddenly stopped working everywhere. If you throw a baseball today, Newton's equations still describe its motion extremely well. If engineers build a skyscraper, launch a satellite, or calculate the orbit of a spacecraft, classical physics remains incredibly accurate. The crisis appeared only when scientists pushed their experiments deeper into the world of atoms. At first, the problems looked minor. Many researchers believed they were simply dealing with missing information or incomplete measurements. New theories would be created, a few equations would be adjusted, and everything would return to normal. That never happened. Instead, every year seemed to reveal another crack in the foundation. One of the biggest cracks appeared when physicists began studying something that sounded surprisingly ordinary: heat. Imagine heating a metal object until it glows. At first, it becomes warm, then it turns red. Keep heating it and the color changes. Eventually, it becomes bright white. This is something humans had observed for thousands of years. Blacksmiths saw it, metal workers saw it. Anyone who had ever watched metal inside a furnace had seen it happen. Scientists wanted to understand exactly why. They began studying what was called blackbody radiation. A blackbody is an ideal object that absorbs all incoming light and then releases energy as radiation. It became a useful model for understanding how hot objects emit light. Researchers measured the radiation coming from heated objects with increasing precision. They expected classical physics to explain the results. Instead, classical physics produced an answer that made no sense. According to the existing equations, a heated object should release more and more energy at shorter and shorter wavelengths. As the wavelength approached the ultraviolet part of the spectrum, the predicted energy output skyrocketed toward infinity. Infinity. Not a very large number, not an unusually high value. Infinite energy. The equations were effectively saying that a warm object should produce limitless amounts of ultraviolet radiation. Clearly, that was impossible. Scientists could perform the measurements directly. Real objects did not behave this way. Furnaces were not flooding rooms with infinite energy. Heated metal was not releasing endless ultraviolet light. Nature was doing one thing while the equations predicted something entirely different. This disaster became known as the ultraviolet catastrophe. The name was not an exaggeration. If the equations were correct, reality should have looked completely different from what anyone observed. If reality was correct, then the equations that had worked so well elsewhere were missing something fundamental. For physicists, this was deeply unsettling. Newtonian physics had been treated almost like the final answer to how nature worked. Yet here was a situation where the theory was failing so badly that it was predicting physically impossible results. Scientists searched desperately for solutions. Many believed the problem had to be somewhere in the calculations. Others thought hidden factors had been overlooked. Some expected a small correction would eventually solve everything. Then a German physicist named Max Planck made a proposal that would change science forever. Planck was trying to solve the blackbody radiation problem. He was not attempting to overthrow physics. In fact, he expected his idea to be a mathematical trick, a temporary fix that would later be replaced by something better. Instead, it opened the door to an entirely new understanding of reality. Planck suggested that energy might not be emitted continuously. That sounds simple today, but at the time it was shocking. Classical physics treated energy like a smooth flow. A system could possess any amount of energy. There were no restrictions, there were no smallest units. Planck proposed something different. What if energy came in tiny packets? What if matter could only absorb or release specific amounts? When he built this assumption into his calculations, something remarkable happened. The ultraviolet catastrophe disappeared. The experimental results suddenly matched the theory. The impossible infinity vanished. For the first time, the measurements made sense. The solution worked so well that scientists could not ignore it. But many still believed there had to be a deeper classical explanation waiting to be discovered. The idea that energy itself might come in discrete units felt too strange. Yet the surprises were only beginning. While physicists were still trying to understand Planck's discovery, another problem emerged. This one involved light itself. For decades, light had been understood as a wave. Experiments seemed to confirm it repeatedly. Waves could interfere with each other, they could spread out, they could produce patterns that matched observations perfectly. The wave theory of light appeared secure. Then researchers began studying something called the photoelectric effect. The setup was straightforward. Light shines onto a metal surface. Electrons are ejected from the metal. At first glance, this did not seem particularly mysterious. Classical physics predicted that brighter light should transfer more energy to the electrons. If enough energy accumulated, electrons would eventually escape. Simple, reasonable, wrong. Experiments revealed behavior that completely contradicted those expectations. Scientists discovered that increasing the brightness of certain light sources did not always eject electrons. You could make the light more intense. You could pour more energy onto the metal. You could keep increasing the brightness. Sometimes nothing happened. Then researchers changed something else. Instead of increasing brightness, they increased the frequency of the light. Suddenly, electrons were emitted immediately, not after a delay, not after energy gradually accumulated, immediately. Even more confusing, a dim light with a high enough frequency could eject electrons, while an extremely bright light with a lower frequency could fail completely. This should not have happened according to classical wave theory. The results made no sense. Scientists now faced another serious problem. The blackbody radiation crisis had already exposed weaknesses in classical physics. Now the behavior of light itself seemed to be challenging the established picture. The situation was becoming difficult to ignore. Something important was missing. That missing piece arrived in 1905. A young patent clerk named Albert Einstein published a paper that would become one of the most important scientific works ever written. Einstein took Planck's idea seriously, much more seriously than many of Planck's own colleagues. Instead of treating energy packets as a mathematical trick, Einstein proposed that light itself might be quantized. In other words, light might arrive in separate packets of energy. Today, we call those packets photons. At the time, the idea sounded almost absurd. Light was supposed to be a wave. Now Einstein was suggesting that it also behaved like individual particles carrying specific amounts of energy. Yet when he applied this idea to the photoelectric effect, everything suddenly fit together. The strange experimental results stopped being strange. If light arrived as individual packets, then each packet carried a specific amount of energy determined by its frequency. Higher frequency meant higher energy. Lower frequency meant lower energy. This explained why brightness alone was not enough. A brighter beam simply meant more photons, but if each photon lacked the minimum required energy, then no electrons would be ejected no matter how many photons arrived. It was like throwing thousands of soft foam balls at a locked door. More balls would not help if none carried enough force individually. A single stronger object could succeed where millions of weaker ones failed. The experiments matched Einstein's explanation perfectly. Electrons appeared instantly because they were interacting with individual photons, not slowly collecting energy from a continuous wave. The higher the frequency, the more energetic each photon became. The mystery vanished. But the larger problem became even more serious. Physics now faced an uncomfortable reality. Two completely different experiments had pointed toward the same conclusion. The universe at very small scales was not behaving according to classical expectations. Energy appeared quantized, light appeared quantized. The smooth, continuous world described by Newtonian physics was beginning to break apart. Scientists could no longer dismiss these results as isolated oddities. They were seeing a pattern suggesting that atoms, light and energy obeyed rules that were fundamentally different from the rules governing planets, baseballs and falling objects. This was not a small adjustment to an otherwise complete theory. This was the beginning of a scientific revolution. Wave function discovery. By the mid-1920s, physics had reached a very strange point. Scientists knew something was wrong with the old picture of reality. The problems with blackbody radiation had refused to go away. The photoelectric effect had shown that light behaved in ways classical physics could not explain. More and more experiments were producing results that seemed impossible if Newton's view of the universe was the whole story. Yet despite all these discoveries, there was still a major problem. Nobody truly understood what was actually happening inside an atom. Physicists could measure things. They could build equations that matched experiments. They could predict certain outcomes. But when they tried to picture what electrons were physically doing, the answers became increasingly confusing. For centuries, people had imagined matter as tiny particles moving through space like miniature versions of planets. It was a natural assumption. After all, everything we see in daily life behaves that way. A baseball follows a path. A bullet follows a path. A car follows a path. If something exists, it seems reasonable to assume it travels from one location to another along a definite route. Scientists expected electrons to behave the same way. The problem was that experiments kept refusing to cooperate. The more researchers studied electrons, the less they looked like tiny balls moving along predictable tracks. Sometimes electrons behaved like particles. That was already established. They could strike detectors at specific locations. They could collide with other particles. They could transfer energy in measurable amounts. But in other experiments, electrons behaved like waves. Not wave-like in some loose or symbolic sense. Actual wave behavior. They produced interference patterns. They spread out. They displayed properties that looked remarkably similar to the behavior of light waves. This created a serious problem. How could something be a particle and a wave at the same time? Those were supposed to be different things. A particle occupies a specific location. A wave spreads across space. A particle follows a path. A wave extends over many possible paths at once. Trying to fit electrons into the old framework was becoming harder every year. Physicists needed a new way of describing what they were seeing. That breakthrough came in 1926 when a young Austrian physicist named Erwin Schrödinger introduced an equation that would become one of the most important achievements in the history of science. At first glance, the equation itself looked like just another mathematical formula. physics was already full of equations. Most people outside the field would not have noticed anything special about it. But what Schrödinger had created was not simply a new calculation tool. He had created an entirely new way of describing reality at the atomic level. The equation allowed physicists to calculate how a quantum system changes over time. It provided a mathematical description of how electrons and other particles behave when they are not being measured. That may sound straightforward, but it represented a dramatic shift in thinking. Before Schrödinger, scientists often tried to imagine electrons as tiny objects moving through space in the same way larger objects move through space. After Schrödinger, that picture became much harder to maintain, because when physicists used the equation, the results did not describe electrons as little particles travelling along fixed paths. Instead, the equation produced something called a wave function. The word sounds technical, but the idea behind it is what truly changed everything. The wave function is a mathematical object that describes all the possible states a quantum system can occupy. Instead of telling you where an electron is located with certainty, it tells you the range of possible locations where it might be found when measured. This was radically different from anything in classical physics. Imagine throwing a baseball across a field. At any moment, you can point to where the baseball is. It has a definite position. Even if nobody is looking at it, the baseball still occupies a specific location. That is how everyday objects behave. Electrons did not seem to behave that way. According to Schrödinger's framework, an electron could not always be described as occupying one precise location before measurement. Instead, it had to be represented by a wave function spread across multiple possibilities. This idea was deeply unsettling to many scientists. Some believed it had to be incomplete. Others assumed there must be hidden details that had not yet been discovered. After all, common sense suggested that objects should have definite positions, whether we measure them or not. But common sense was starting to lose its grip on the atomic world. The experiments kept pointing in the same direction. And the wave function kept producing the correct answers, again and again. Researchers would calculate what should happen using Schrödinger's equation. Then they would perform experiments. The predictions matched reality with extraordinary accuracy. That success could not be ignored. What made the wave function especially powerful was that it explained behaviours that had previously seemed impossible. Take the famous double-slit experiment. Scientists could fire electrons one at a time toward a barrier containing two narrow openings. Behind the barrier was a screen that recorded where each electron landed. Classically, the outcome should have been simple. An electron should pass through the left slit or the right slit, one or the other. That is how particles behave, yet the actual results told a different story. When enough electrons were sent through the apparatus, they gradually formed an interference pattern. Interference patterns are normally associated with waves. Water waves produce them, light waves produce them. The pattern suggested that each electron was somehow interacting with both possible paths. This was difficult to explain if the electron was simply a tiny object moving along a single route. The wave function provided a different picture. Instead of assigning the electron one definite path before measurement, the wave function evolved through both openings simultaneously. The mathematical description included both possibilities at the same time. This was not because scientists lacked information. It was not because the electron was secretly choosing a path while hiding the answer. The mathematics itself evolved across multiple possibilities. That distinction became incredibly important. Many people hear quantum physics and immediately imagine particles making choices. It is an understandable misunderstanding because choice is how humans think about uncertain situations. If a person approaches a fork in the road, they choose one direction. If a coin is tossed, it lands one way or another. We instinctively imagine quantum particles behaving similarly. But Schrödinger's equation does not describe particles making decisions. There is no tiny electron stopping to think about which route it prefers. There is no hidden mind inside the particle weighing alternatives. The mathematics describes something very different. The wave function evolves according to strict rules. It spreads, changes, combines, and interacts based on the equation itself. The process is completely mathematical. In fact, one of the most remarkable aspects of Schrödinger's equation is how deterministic it is. That may sound surprising because quantum mechanics is often associated with randomness. But before measurement enters the picture, the wave function evolves in an orderly and predictable way. Given the current wave function and the conditions of the system, physicists can calculate how the wave function will develop in the future. The evolution follows precise mathematical rules. There is no randomness in that part of the process. This created a fascinating situation. The underlying mathematical evolution appeared smooth and predictable, yet measurements produced individual outcomes. Somewhere between the evolving wave function and the observed result lay one of the deepest mysteries in science. But before physicists could even tackle that problem, they first had to accept what the wave function was telling them. And what it was telling them was increasingly difficult to ignore. Electrons were not behaving like miniature planets orbiting a nucleus in neat classical paths. The old images that appeared in early textbooks were useful simplifications, but they did not reflect what the mathematics actually described. The wave function painted a much stranger picture. Inside an atom, an electron was better understood as a spread of possibilities described by mathematical waves rather than a tiny object following a fixed orbit. This new understanding solved several long-standing problems. Classical models of atoms had struggled to explain stability. According to older theories, orbiting electrons should continuously radiate energy and spiral into the nucleus. Atoms should collapse. Clearly, they did not. Matter exists. Atoms remain stable. The wave function offered a completely different framework. Instead of imagining electrons orbiting like planets, physicists could describe them as existing in specific quantum states, determined by the solutions of Schrödinger's equation. Suddenly, many puzzling features of atomic structure began making sense. Chemical behavior became easier to understand. Atomic spectra could be calculated. The organization of the periodic table gained a deeper explanation. What had previously seemed like disconnected observations started fitting together into a coherent picture. And the wave function sat at the center of it all. Yet despite its success, the concept remained difficult to visualize. People naturally want a picture. They want to imagine what an electron actually looks like. They want something familiar. A tiny ball, a tiny sphere, a miniature object moving through space. The wave function refuses to provide that comfort. It does not offer a simple visual image. Instead, it offers a mathematical description that predicts outcomes with astonishing precision. In many ways, this marked a turning point in the history of science. For centuries, physics had often progressed by building intuitive mechanical pictures of how nature worked. Gears, forces, trajectories, and motions could all be imagined directly. Quantum mechanics forced physicists into unfamiliar territory. The mathematics was working better than intuition. The equations were revealing a reality that human instincts were not designed to understand, and that reality became even more unsettling as scientists explored larger and larger systems. Because the wave function was not limited to electrons, the same mathematical framework could describe atoms. It could describe molecules. It could describe light. It could describe collections of particles interacting together. The deeper researchers pushed the theory, the broader its reach became. What started as a tool for understanding atomic behavior began looking more like a description of nature itself. The measurement problem. By the time physicists accepted that the wave function was successfully describing the behavior of atoms and particles, a new problem appeared almost immediately. In many ways, it was an even bigger problem than the ones that had come before. The mathematics was working. That was never the issue. Again and again, experiments matched the predictions. Scientists could calculate probabilities with astonishing accuracy. They could predict where electrons might appear. They could explain atomic behavior. They could describe interactions that classical physics had completely failed to understand. The equations were succeeding. But there was one question that nobody could answer. What exactly happens when a measurement takes place? At first, that may not sound like a difficult question. In everyday life, measuring something feels completely ordinary. You measure the temperature outside. You check your weight on a scale. You look at the time on your phone. None of these activities seem mysterious. But quantum physics was not asking about measurement in the everyday sense. It was asking something much deeper. When does a possibility become an actual outcome? That question sat right at the center of quantum mechanics. And the more scientists looked at it, the stranger it became. Imagine an electron described by a wave function. According to the mathematics, that wave function can spread across multiple possibilities. It can represent different positions the electron could be found in. It evolves smoothly through time according to the rules laid out by Schrödinger's equation. Everything seems clear so far. Then a detector is introduced. The detector measures the electron. Suddenly, only one outcome appears. The detector does not record several possibilities at once. It records one specific result. Maybe the electron is detected here. Maybe it is detected there. But the measuring device always produces a single answer. And this is where the trouble starts. Before measurement, the mathematics describes multiple possibilities. After measurement, only one result remains visible. What happened in between? For decades, that question has remained one of the biggest unresolved issues in physics. The strange part is that the mathematics itself seems to tell two different stories. On one hand, Schrödinger's equation describes a smooth and continuous evolution. The wave function changes over time in a predictable way. Nothing in the equation says that possibilities should suddenly disappear. The evolution is continuous. The evolution is orderly. The evolution follows precise mathematical rules. Then measurement enters the picture. Suddenly, physicists start talking about something called collapse. The idea sounds simple enough. According to the traditional view, when a measurement occurs, the wave function collapses. Instead of containing multiple possibilities, it suddenly reduces to one observed outcome. The electron is detected. The other possibilities vanish. The system now has a definite state. Problem solved. At least, that is what it seemed at first. The trouble is that nobody could explain exactly how this collapse happens. Even worse, nobody could explain precisely when it happens. This led physicists into a problem that sounds surprisingly basic. What actually counts as an observation? That question may seem strange because most people immediately think they know the answer. An observation is when somebody looks at something. Simple. Except quantum physics does not work that way. Human eyes are not special in the equations. Human awareness is not part of the mathematics. The wave function does not contain a term labeled person looking. So scientists began asking more precise questions. Does observation happen when a detector records information? Does it happen when a photon strikes a sensor? Does it happen when a computer stores data? Does it happen when a scientist reads the results? Does it happen when information reaches the brain? Each possibility creates new complications. To see why this became such a serious problem, imagine a simple experiment involving an electron detector. An electron enters the apparatus. The detector records a result. Nobody is present. The laboratory is completely empty. The data is stored automatically. Hours later, a scientist enters the room and checks the results. When did the measurement occur? Did it happen when the detector recorded the signal? Did it happen when the information was saved? Or did it happen later, when the scientist looked at the screen? The equations themselves do not provide a clear answer. That uncertainty became deeply uncomfortable for physicists. Science is supposed to describe physical processes objectively. The laws of nature should not depend on whether someone is paying attention. Yet discussions about measurement kept dragging researchers toward questions they never expected to face. Some scientists argued that observation simply means interaction. Whenever a quantum system interacts with a measuring device, the measurement occurs. This sounds reasonable. But then another question appears. What exactly qualifies as a measuring device? A detector is made of atoms. The electron is made of quantum particles. The detector itself should also obey quantum rules. If both the electron and the detector are quantum systems, then why should one cause collapse while the other does not? The problem starts spreading. Suppose the detector becomes linked with the electron. Now the detector is part of the quantum description. Then a computer records the detector's result. The computer becomes part of the quantum description too. Then a scientist reads the computer. Now the scientist becomes part of the system. Every attempt to define a clear boundary seems to push the problem further away instead of solving it. This became known as the measurement problem. Not because physicists could not perform measurements. Measurements happen every day. The problem was understanding what the measurements actually mean within the mathematical framework of quantum mechanics. The deeper researchers looked, the stranger the situation became. One of the reasons this issue became so important is because Schrödinger's equation itself never mentions collapse. That fact often surprises people. The equation governs how the wave function evolves through time. It works incredibly well. It successfully predicts countless experimental results, yet nowhere in the equation does nature suddenly stop and eliminate possibilities. The mathematics simply keeps evolving. This creates an uncomfortable tension. If the equation is correct, then why introduce collapse at all? And if collapse is real, where does it come from? Physicists found themselves caught between two very different pictures of reality. The first picture became the traditional approach. In this view, wave functions evolve according to Schrödinger's equation until a measurement occurs. At that moment, collapse takes place and one outcome becomes reality. This interpretation became extremely influential because it matched practical observations. Scientists perform experiments. They get definite results. The approach seemed to fit what laboratories actually observed, yet it left important questions unanswered. Most importantly, it never clearly explained what physical mechanism causes collapse. The second picture took a very different path. Instead of asking what causes collapse, some physicists began asking a more radical question. What if collapse never happens? At first, this idea sounded outrageous. After all, measurements appear to produce single outcomes. But the more researchers examined the mathematics, the harder it became to find any direct evidence for collapse itself. The evidence showed that measurements occur. The evidence showed that observers see definite results, but showing definite outcomes is not necessarily the same thing as proving that the wave function physically collapses. That distinction became increasingly important. Imagine following Schrödinger's equation without adding anything extra. The wave function evolves. The detector becomes linked with the quantum system. The environment becomes linked as well. Everything continues evolving according to the same mathematical rules. No collapse is inserted. No special event occurs. The equations simply continue. Some physicists found this possibility attractive because it treated quantum mechanics consistently. The same rules applied everywhere. There was no need to suddenly introduce a separate collapse process that existed outside the equation. But this raised a new challenge. If collapse never happens, then why do people observe only one outcome? That question would eventually become one of the central motivations behind later interpretations of quantum mechanics, including the ideas that will become important later in this documentary. For now, though, physicists were facing a simpler but deeply unsettling reality. Nobody knew whether collapse was real. Nobody knew exactly what observation meant. Nobody knew where the boundary between quantum possibilities and everyday reality should be placed. And this was not a fringe issue. It sat directly at the heart of the theory. Every successful quantum calculation eventually led back to the same mystery. The wave function evolves, measurements occur, results appear. What happens in between? As experimental technology improved throughout the 20th century, this question became even harder to avoid. Scientists began building increasingly sophisticated instruments capable of probing quantum systems with extraordinary precision. They could isolate particles, they could manipulate atoms, they could perform experiments that earlier generations would have considered impossible. Yet every advance seemed to reinforce the same puzzle. The mathematics continued working beautifully. The interpretation remained unclear. Researchers could predict outcomes with incredible accuracy while still disagreeing about what the theory was actually saying about reality. That unusual situation is one of the reasons quantum mechanics remains so fascinating today. Most scientific theories become easier to understand as evidence accumulates. Quantum mechanics became more successful while simultaneously generating deeper questions. Every new experiment strengthened confidence in the equations. At the same time, those same experiments kept shining a spotlight on the unresolved issue of measurement. The conflict between collapse and no collapse views was not a minor disagreement over terminology. It represented two very different ways of thinking about what the wave function actually is and what happens during observation. One side argued that possibilities genuinely reduced to a single outcome. The other side questioned whether any reduction was necessary at all. Both sides could point to the same experiments. Both sides could use the same mathematics. Both sides could produce predictions matching observations. And that is what made the problem so difficult. This was not a case where one group had data and the other did not. The disagreement emerged from the success of the theory itself. Quantum mechanics worked so well that physicists were forced to confront the implications of their own equations, and those implications refused to provide a simple answer to one of the most basic questions imaginable. When a quantum system is measured, what actually happens? Key experimental evidence. If quantum mechanics had remained only a collection of strange equations on paper, very few people would still be talking about it today. Scientists would have treated it as an interesting mathematical exercise, argued about it for a few years, and eventually moved on. What gave quantum mechanics its power was not the mathematics alone. It was the fact that nature kept agreeing with it, again and again, in laboratory after laboratory, across decades of testing, across completely different types of experiments. The theories were strange, but the evidence refused to go away. This is important to understand because when people first hear about concepts like superposition or wave functions, they often assume physicists are simply guessing. The ideas sound so far removed from everyday experience that it is tempting to think they exist only because scientists have chosen to interpret reality in an unusual way. That is not what happened. The reason physicists take these ideas seriously is because experiments kept forcing them to. One experiment in particular became one of the most famous in the history of science. It is simple enough to describe to a child, yet even today it continues to challenge some of our deepest assumptions about how reality works. The experiment begins with a barrier. Nothing complicated, just a wall with two narrow openings cut into it. Behind the wall is a screen capable of recording impacts. If you throw small objects through the openings, you can predict what should happen. Imagine firing tiny pellets at the barrier. Some pellets pass through the left opening, others pass through the right opening. Eventually, two clusters appear on the screen behind the barrier. Simple, straightforward, exactly what common sense expects. Now imagine replacing the pellets with waves. Water waves provide a useful example. When waves pass through two openings, the waves spread out from both slits and overlap. In some places they reinforce each other. In other places they cancel each other out. The result is an interference pattern. Instead of two simple clusters, you get a series of bright and dark regions. That outcome also makes sense. Particles produce one pattern, waves produce another. The distinction seems clear. Then physicists decided to run the experiment using electrons. At first, the expectation was obvious. Electrons are particles. They should behave like particles. Fire enough electrons at the barrier and 2 clusters should appear on the screen. That is not what happened. Instead, the screen gradually revealed an interference pattern, the same type of pattern associated with waves. This was already surprising enough, but scientists pushed the experiment further. Some critics argued that the result might simply be caused by electrons interacting with each other. After all, if large numbers of electrons were passing through the apparatus at the same time, perhaps they were somehow creating the interference collectively. It was a reasonable objection. So researchers changed the experiment. Instead of sending many electrons through the apparatus, they fired them one at a time. 1 electron enters. A detection appears on the screen. Then another electron enters. Another detection appears. Then another, and another, and another. The process continues for thousands of individual electrons. At first, the screen looks random. Tiny dots appear scattered across its surface. Nothing unusual seems to be happening. Then something remarkable begins to emerge. As more and more detections accumulate, a familiar pattern starts taking shape, an interference pattern, the same interference pattern that appeared when large numbers of electrons were used. This immediately raises a difficult question. How can a single electron contribute to an interference pattern if there are no other electrons present to interfere with? That question became one of the defining mysteries of quantum mechanics. The evidence seemed to suggest that each electron was somehow interacting with multiple possibilities associated with its own wave function. The interference pattern was not being created by groups of electrons interacting with one another. The pattern emerged even when electrons passed through the apparatus individually. Think about how strange that really is. An electron enters the system, only 1 electron, not a crowd, not a stream, 1. Yet when enough individual events are collected, the overall pattern looks exactly like something produced by waves spreading through both openings. This result has been repeated countless times. Different laboratories, different equipment, different researchers. The outcome remains the same. The interference pattern appears, and that pattern tells physicists something important. Before measurement, the electron cannot be described adequately as a tiny object following one definite path through the experiment. The evidence points toward a more complicated reality, a reality where multiple possibilities remain active until measurement occurs. Naturally, scientists wanted to know more. If the electron appears connected to multiple paths, can we determine which path it actually took? At first glance, that seems like a simple question. Just place detectors near the slits. Watch what happens. Find out which opening the electron passes through. Problem solved. So researchers did exactly that. They added measuring devices capable of identifying the electron's path. Then they ran the experiment again. This is where things became even stranger. The interference pattern disappeared. Not weakened, not slightly altered. Gone. Instead of producing the familiar wave-like pattern, the electrons now behaved more like ordinary particles moving through one slit or the other. The moment information about the path became available, the interference vanished. This observation would become one of the most important pieces of evidence in all of quantum physics. Because the change was not caused by physically blocking the electron. The detectors were not stopping it. The experiment still allowed electrons to pass through the apparatus, yet the pattern changed completely once path information entered the picture. The wave-like behavior seemed connected to the absence of which path knowledge. Whenever information revealed the route taken by the electron, the interference pattern disappeared. Whenever that information was unavailable, the interference pattern returned. Researchers repeated the experiment in countless variations. The details changed. The outcome did not. Again and again, interference depended on whether path information could exist. This finding became central to the measurement problem discussed earlier. Something about measurement was affecting the behavior of the system. But what exactly? Was the electron physically changing? Was the wave function collapsing? Was some deeper process taking place? The experiments provided evidence. The interpretation remained controversial. As technology improved, scientists began designing increasingly sophisticated versions of the double-slit experiment. They wanted to test the limits of these strange effects. They wanted to know whether the disappearance of interference truly depended on information itself, or whether some overlooked physical process was responsible. That search eventually led to one of the most famous modern experiments in quantum physics, the delayed choice quantum eraser. Even the name sounds unusual, and the experiment behind it is every bit as surprising. To understand why it caused such excitement, imagine modifying the double-slit experiment once again. An electron or photon enters the apparatus. The particle encounters multiple possible paths. Detectors and optical devices are arranged to preserve or erase information about those paths. The key twist is that the decision about whether path information remains available can be made after the particle has already entered the system. At first glance, this sounds impossible. Common sense immediately objects. Surely what happened in the past cannot depend on something decided later. Yet the delayed choice experiments appeared to challenge exactly that intuition. When physicists first proposed these ideas, many people misunderstood what was being claimed. Some assumed the experiments proved information was travelling backward through time. That interpretation generated enormous attention. It also generated enormous confusion. The actual situation is more subtle. The experiment does not show messages being sent into the past. It does not allow communication backward through time. It does not rewrite history. What it does show is that the way quantum systems are described becomes difficult to fit into ordinary stories about particles following fixed paths. The delayed choice quantum eraser forces researchers to confront an uncomfortable possibility. Perhaps the electron never possessed a simple classical path in the first place. Perhaps asking which slit it really went through before measurement is already the wrong question. This is where the experiment becomes so powerful. It pushes directly against the assumptions people naturally bring into physics. We are used to thinking that objects have definite histories. We assume a baseball follows one route through space. We assume a bullet travels along one trajectory. We assume a car takes one road rather than another. Quantum systems do not always fit comfortably into that framework. The delayed choice experiments highlight this tension with remarkable clarity. As researchers analysed the results, one message became increasingly difficult to ignore. The mathematics describing quantum systems often works best when possibilities remain part of the description until measurement-related information becomes available. That idea sounded strange decades ago. It still sounds strange today. Yet the experimental evidence repeatedly points in the same direction, and the evidence became even stronger as scientists improved their ability to isolate quantum systems from their environments. One of the biggest challenges in these experiments involves preserving interference. Quantum systems are incredibly sensitive. Tiny interactions with surrounding particles can disrupt the conditions required for interference to appear. A stray photon, a molecule of air, a small environmental disturbance. Any of these can influence the outcome. Researchers discovered that maintaining interference requires careful control. The system must remain isolated enough that path information does not leak into the environment. This discovery revealed something important. Interference does not simply disappear for no reason. It disappears when information about the alternatives becomes available. That information does not necessarily need to reach a human observer. This point is often misunderstood. The universe does not wait for a person to look. What matters is whether information about the path becomes physically encoded somewhere. If path information exists in a form that can, in principle, be recovered, interference is lost. If that information is erased or never becomes available, interference can reappear under the right conditions. This distinction became one of the most significant findings in modern quantum experiments. It shifted attention away from human observation and toward physical information itself. The consequences were profound. Scientists began viewing measurement less as an act of conscious observation and more as a process involving the transfer and storage of information. This perspective helped explain why interference patterns disappear when systems become entangled with their surroundings. The environment effectively records information. Once that happens, the conditions necessary for interference are destroyed. This understanding emerged gradually through decades of experimental work. Each new variation of the double-slit experiment revealed additional layers of complexity. Each refinement pushed researchers further away from classical assumptions and deeper into the strange territory governed by quantum mechanics. What makes these experiments so important is that they are not isolated curiosities. They form a connected body of evidence pointing toward the same underlying reality. The behavior of single electrons, the disappearance of interference under measurement, and the results of delayed choice quantum eraser experiments all challenge the idea that microscopic particles simply travel along fixed paths, waiting to be discovered. Instead, the evidence consistently supports a framework in which possibilities play an active role before measurement, where information matters in unexpected ways, and where the behavior of quantum systems cannot always be reduced to the familiar stories we use to describe objects in everyday life. The many worlds interpretation emerges. By the time physicists reached the middle of the 20th century, quantum mechanics was already proven to work in every serious experiment, from simple atomic tests to highly controlled laboratory setups. Yet there was still a deep problem sitting inside the theory that no one could ignore for long, because the equations described a smooth and predictable evolution of quantum systems, while actual measurements always produce single, definite outcomes. And this gap between continuous mathematics and single results kept pushing scientists into uncomfortable questions about what really happens when a quantum system is observed. One of the most important turning points came in 1957, when a young physicist named Hugh Everett III introduced an idea that did not try to fix quantum mechanics by adding something new, and did not try to modify the equations, but instead took the equations exactly as they were written and followed them to their full logical outcome, without inserting any extra rules for measurement or collapse. And this decision alone made his approach stand out in a field where most explanations still relied on adding special assumptions whenever observation occurred. Everett started with a simple but powerful claim, which is that the wave function described by the Schrödinger equation never stops evolving and never collapses under any condition. Because according to the mathematics, there is no point in the equation where it says a system must suddenly reduce to one outcome. And if the equation is correct for all physical systems, then it should also be correct for measuring devices and observers, since they are made of the same kind of particles that follow the same quantum rules. This idea removed one of the central assumptions that have been widely used in quantum physics for years, which is the idea of wave function collapse, where a system evolves through multiple possibilities, but then suddenly jumps into a single outcome when a measurement takes place, because Everett argued that this jump was not supported by the mathematics, and instead appeared only because of how people were interpreting the results of experiments, rather than what the equations themselves were actually saying. To understand what Everett was proposing, it helps to go back to the idea of a quantum event, where a system can evolve into multiple possible outcomes according to its wave function. And instead of saying that only one of those outcomes becomes real while the others disappear, Everett's approach says that all outcomes continue to exist, but become separated from each other in a way that prevents any interaction between them. And this separation is not an assumption, but something that naturally follows from how quantum systems interact with their environment. In this picture, every time a quantum event happens, the universe does not select one result and erase the rest, but instead the wave function evolves into a larger structure where each possible outcome develops independently. And once these outcomes interact with the surrounding environment, they become effectively isolated from each other through a process known as decoherence, which means that each outcome stops interfering with the others even though they are still part of the same overall wave function. This leads to the core idea that became known as branching, where each quantum event produces multiple non-communicating branches of reality. And these branches are not separate physical universes created from nothing, but are instead different parts of the same universal wave function that no longer interact after decoherence has taken place. So each branch continues forward on its own, without any ability to exchange information with the others. In this framework, there is no need for wave function collapse because nothing is being removed from the system, and instead of one outcome becoming real while others vanish, all outcomes continue to exist as part of the evolving quantum state. And what we experience as a single outcome is simply the result of being inside one branch where the other branches are no longer accessible in any practical way due to decoherence. This approach becomes even clearer when looking at how Everett treated measurement itself, because instead of seeing measurement as a special process that changes the rules of physics, he treated it as just another quantum interaction, where the measuring device becomes entangled with the system being measured. And this entanglement spreads through the environment so that each possible result of the measurement becomes tied to a different state of the measuring device, and eventually to different states of the observer as well. For example, if an electron has two possible outcomes when measured, the wave function evolves into a combined state where both outcomes exist, and the measuring device becomes correlated with both outcomes at the same time. And then the observer who reads the device also becomes part of this combined system, so that the final state contains multiple versions of the observer, each one experiencing a different outcome. And these versions do not interact with each other because decoherence prevents any overlap between them. This is not described as a physical splitting of matter in space, but as a splitting of the wave function into distinct branches that evolve independently, and each branch contains a consistent history where one specific outcome has occurred. So within each branch, the observer experiences a single, definite result, even though the full quantum description contains all possible results at once. The mathematical foundation for this idea is the same Schrödinger equation that governs all quantum systems, and Everett's key point was that this equation should not be broken or modified when a measurement occurs, because there is no evidence in experiments that suggests the equation stops working at any point, and instead it continues to produce accurate predictions whether the system is an electron, a molecule, a measuring device, or a human brain, since all of these are ultimately composed of quantum particles. This leads to the concept of the universal wave function, which is the idea that the entire universe can be described as a single wave function evolving according to the Schrödinger equation without exception. And in this view, there is no special boundary between the microscopic quantum world and the macroscopic classical world, because everything is part of the same underlying mathematical structure that evolves continuously over time. The universal wave function contains every possible configuration of matter in the universe, and as time passes, it develops into a complex structure where different outcomes of quantum events become separated into non-interacting branches, and each branch follows its own consistent history, where events appear definite and classical, even though the underlying description remains fully quantum in nature. What makes this idea especially powerful is that it does not change any of the predictions of standard quantum mechanics, because all experimental results remain exactly the same, whether you assume collapse or not. And this means Everett's approach does not require new equations or new forces or new rules, but instead relies only on the existing Schrödinger equation applied consistently to everything without exception. However, this also created one of the main reasons why the idea was not widely accepted at the time, because many physicists preferred interpretations that included wave function collapse, even though collapse was not part of the original equations, since collapse provided a simple way to explain why we observe single outcomes in experiments without having to think about multiple branches, or, multiple versions of observers existing in different parts of the wave function. Another major reason Everett's idea was ignored for many years is that it did not produce any new testable predictions that differed from other interpretations, because whether you assume collapse or branching, the observable results in experiments remain the same, which made it difficult for physicists to decide between interpretations based on experimental evidence alone and, in physics where testability is extremely important, ideas that cannot be distinguished by experiment often struggle to gain immediate acceptance. At the time Everett introduced his work, the dominant view in quantum physics was the Copenhagen interpretation, which treated the wave function as a tool for predicting probabilities and assumed that measurement causes a real physical collapse into a single outcome. And this view had already become deeply established in the physics community through the work of early pioneers of quantum mechanics. So any alternative approach had to compete not only with mathematics, but also with decades of scientific tradition and teaching. Because of this dominance, Everett's proposal was initially treated with skepticism, and many physicists found the idea of multiple non-communicating branches difficult to accept, not because the mathematics was incorrect, but because it challenged the intuitive picture of a single, unique reality that most people naturally assume when thinking about physical systems, even though quantum experiments themselves do not require that assumption in order to match their results. Over time, however, the idea began to resurface as physicists studied decoherence more carefully and realized that the environment naturally causes quantum systems to split into effectively independent branches without needing any special collapse rule. And this discovery gave new support to Everett's original framework by showing that the branching structure he described could emerge directly from standard quantum mechanics without additional assumptions. This renewed interest did not immediately settle the debate, but it did shift attention toward the possibility that the wave function might always evolve smoothly according to the Schrödinger equation, while the appearance of single outcomes could come from the way information spreads through the environment and becomes inaccessible between branches, rather than from any sudden physical collapse occurring during measurement. As research continued, the universal wave function idea became an important part of discussions about the foundations of quantum mechanics, because it offered a way to describe all physical systems under a single consistent rule without needing to define a special role for observation. And this consistency became one of its most appealing features for physicists who preferred theories that avoid arbitrary boundaries between different parts of nature. The idea of multiple branches evolving without interaction also changed the way physicists thought about quantum events at a fundamental level, because instead of seeing each event as producing a single outcome selected from a set of possibilities, it became possible to think of each event as generating a structure where all outcomes continue to exist in separate branches, each one following the same physical laws, but remaining isolated from the others due to decoherence and loss of interference. This perspective keeps returning to the same mathematical foundation, which is that the Schrödinger equation governs the evolution of the wave function at all times, without interruption. And since the equation does not contain any built-in mechanism for collapse, Everett's interpretation takes the position that no such mechanism is needed, and everything that happens in quantum mechanics can be explained through continuous evolution, combined with branching caused by interactions with the environment. As this framework developed further, it became closely linked with experimental work on decoherence, which showed in detail how quantum systems lose coherence when they interact with surrounding particles, and how this process naturally separates different outcomes into non-interacting structures that behave like independent classical histories, even though they remain part of the same overall quantum state. This connection between theory and experiment gave the many worlds approach a stronger physical grounding, because it was no longer just a reinterpretation of equations, but also a way of understanding how real laboratory systems behave when they become large, complex, and influenced by their environment in ways that prevent quantum interference from being observed at macroscopic scales. Even with this growing support, the interpretation continued to face resistance. mainly because it challenged the idea that there is only one observed outcome for each measurement event, and because it replaced the familiar concept of collapse with a picture where all outcomes persist in separate branches that cannot communicate, which is mathematically consistent, but still difficult to reconcile with everyday intuition about a single shared reality experienced by all observers. Despite this resistance, the framework remains directly tied to the same equations that successfully describe every confirmed quantum experiment, and it continues to be studied as one of the major ways of understanding what the wave function represents when it evolves without any special exceptions for measurement or observation. What infinite U's actually means in physics. The infinite U does not describe physical duplicates being created in space or bodies splitting like cells, but instead describes how the mathematical structure used in quantum mechanics evolves when applied to systems that interact with their environment at every moment. And to understand what this actually means, it is important to stay close to how the physics describes the process rather than how the imagination tries to picture it. The key starting point is that quantum mechanics does not describe reality as a single, fixed outcome that unfolds step by step in a simple classical way, but instead describes systems using a wave function that contains all possible outcomes allowed by the equations. And as long as the system is isolated, this wave function evolves smoothly under the Schrödinger equation. But in real conditions, no system is ever fully isolated because everything interacts with something else. And those interactions are what slowly reshape the wave function into separate parts that no longer influence each other in any meaningful way. This is where the idea of branching comes in. But branching here does not mean physical splitting, like objects breaking apart. And it also does not mean copies appearing in space or time in a literal sense, because space and time continue to evolve normally. But what changes is the structure of the wave function itself, since interactions with the environment cause the wave function to separate into parts that behave as if they are independent, even though they are still part of the same underlying quantum description. To be precise, quantum branching refers to what happens when decoherence takes place, and decoherence is the process that happens when a quantum system becomes entangled with its environment in such a way that the different possible outcomes stop interfering with each other. And once interference is lost, the different parts of the wave function evolve separately without exchanging information, which means that each part follows its own consistent history that cannot affect the others in any practical way. This is very different from duplication in space, because nothing is being copied or moved into different locations, and it is also different from objects travelling through time and splitting into multiple futures in a classical sense, because there is no single timeline that physically divides. Instead, what happens is that the mathematical description of the system naturally evolves into multiple non-interacting components that exist within the same overall framework but behave independently due to the loss of coherence between them. To understand why this separation happens, it is necessary to look at how quantum systems interact with their surroundings, because even a small system, like a particle, is constantly colliding with air molecules, emitting or absorbing photons, and interacting with countless environmental factors. And each of these interactions carries away information about the system. And once that information spreads into the environment, it becomes impossible for the different quantum possibilities to remain connected in a way that allows interference to occur. This process is called decoherence, and it plays a central role in turning quantum possibilities into what looks like classical reality, because before decoherence, a system can exist in a superposition where multiple outcomes remain connected in the wave function. But after decoherence, those outcomes become effectively separated because the environment has recorded information about them in different ways, and once that recording happens, the system no longer behaves like a single, coherent wave that can recombine and interfere with itself. The important detail is that decoherence does not destroy any part of the wave function, because the full mathematical description still contains all outcomes, but what it does is spread the information about those outcomes into the environment in such a way that they cannot recombine or influence each other again. Which means that from a practical point of view, each outcome becomes isolated and behaves like a separate history, even though it remains part of the same underlying quantum structure. This is why physicists often describe the result as independent histories, because once decoherence has taken place, each branch of the wave function evolves as if the others no longer exist, even though they are still present in the full mathematical description. And this is not due to any missing information or hidden variables, but is a direct result of how quantum interactions distribute information across large systems in a way that makes interference impossible to recover at macroscopic scales. When this idea is applied to systems that are larger than simple particles, the same rules still apply, because everything in the universe is ultimately made of quantum components, and each interaction between those components has the potential to produce branching behavior. So over time, the wave function does not remain a simple structure, but instead becomes an extremely complex network of branches that represent different possible outcomes of all the quantum events that have occurred. This leads directly to the question of how to describe something as complex as a human being within this framework, because a human brain is not a single object, but a highly complex physical system made of trillions of interacting particles, and each of those particles is constantly undergoing quantum interactions with its surroundings, which means that the brain is always part of a constantly evolving quantum system that is subject to the same rules of superposition and decoherence as any other physical system. From this perspective, the brain can be described as a physical system that processes information through electrical and chemical signals. But at the deepest level, those signals are carried by particles that follow quantum rules. And at many points during brain activity, there are processes that depend on microscopic events where quantum probabilities can play a role, especially when those events are amplified through larger biological processes that lead to stable macroscopic outcomes. And this is where branching becomes relevant to how different possible outcomes of those microscopic events evolve over time. These microscopic quantum events are often referred to as decision points, in the sense that they lead to different physical outcomes, not because they involve conscious choice at the quantum level, but because they are points where multiple physically allowed outcomes exist according to quantum rules. And once one of these outcomes becomes amplified through neural processes, it can influence larger patterns of brain activity that lead to different macroscopic states, each of which corresponds to a different branch of the overall wave function. It is important to be precise here, because the brain itself is not making quantum decisions in the sense of choosing between possibilities. Since quantum mechanics does not assign decision-making ability to particles or systems, instead, what happens is that quantum events evolve according to the wave function and then become part of larger physical processes that amplify the differences between possible outcomes. And once these differences are amplified and recorded in the environment, through decoherence, the different outcomes no longer interact and begin to evolve independently. In this way, what is sometimes described informally as multiple versions of a person does not refer to physical copies appearing in space, but refers to different branches of the wave function where different outcomes of quantum events have led to different physical states of the same underlying system, and each branch contains a complete and consistent version of the physical world. That includes a version of the person experiencing that branch as if it were the only outcome that occurred. These branches are not created all at once in a single moment, but instead form continuously over time as quantum events occur throughout the universe, because every interaction that involves quantum uncertainty has the potential to produce multiple outcomes that then evolve separately once decoherence takes place. And since such interactions are happening constantly at all scales, the branching structure of the wave function is not static, but continuously growing as new events add new layers of possible outcomes. This leads to the idea of a branching tree structure, where each quantum event adds new branches to an already existing structure, And these branches are not separate universes created from nothing, but are parts of a single evolving wave function that contains all possible outcomes of all events. And each branch continues forward independently once decoherence separates it from other branches, creating a structure that grows more complex over time without any need for collapse or selection of a single outcome. It is also important to understand that this branching is not infinite in a simple and literal sense at any single moment, because it is not as if a fixed number of copies suddenly appear at once. Instead, the number of branches increases gradually as more quantum events occur. And since quantum interactions happen constantly throughout the universe, the branching process is continuous and ongoing rather than a single event that happens once and then stops, which means that the structure is better understood as an evolving network of diverging histories rather than a static set of parallel worlds. What makes this idea especially significant in physics is that it does not introduce anything new beyond the standard equations of quantum mechanics, because the entire structure of branching and independent histories emerges naturally from applying the Schrödinger equation to systems that interact with their environment. And decoherence explains why these branches stop interfering with each other, so the full behavior can be derived from known physical laws, without adding extra rules or special mechanisms for measurement. At the same time, this description changes how one interprets what the wave function represents, because instead of treating it as a tool for calculating probabilities about a single outcome, it becomes a description of a larger structure that contains all possible outcomes as part of its evolution, and each outcome exists in a different branch that follows the same physical laws, but remains isolated due to decoherence and the irreversible spreading of information into the environment. As this framework is applied to more complex systems, the same principles continue to hold, because whether the system is a single particle, a group of atoms, or a large biological structure, the same quantum rules govern its evolution. And the difference lies only in how quickly decoherence occurs and how strongly the environment separates different outcomes into independent branches that no longer interact in any observable way. The experiments that make this plausible. For a long time, scientists believed there was a clear boundary between the quantum world and the classical world, where atoms and electrons followed strange rules, while larger objects followed normal, predictable rules. But modern experiments have been steadily breaking that idea by showing that quantum behavior can survive in systems that are much larger than anyone expected, as long as the system is carefully isolated from its surroundings, so that unwanted interactions do not destroy the delicate conditions needed for quantum effects to appear. One of the strongest early signs that quantum behavior can exist in larger systems comes from experiments involving molecules, especially large organic molecules that contain many atoms joined together in complex structures. Because these molecules are not simple particles, but extended systems with internal structure, and yet they can still show behavior that is only possible if their entire state is treated as a quantum wave rather than a classical object moving along a single path. In these experiments, scientists send beams of large molecules through carefully designed setups that resemble versions of the double-slit experiment, and instead of behaving like solid objects that simply pass through one path or the other, the molecules produce interference patterns that can only be explained if their wave-like nature remains intact while they travel through the apparatus. Which means that even systems made of hundreds or thousands of atoms can still exist in superposition states under the right conditions. This is important because it directly challenges the idea that quantum effects are limited to the microscopic world, since these molecules are large enough that classical intuition would expect them to behave like tiny pieces of matter following definite trajectories, yet the experiments show that their behavior depends on maintaining coherence across the entire system. And when that coherence is preserved, the wave function describing the molecule evolves in a way that allows interference between different possible paths, just like it does for single particles. The key difficulty in these experiments is not creating quantum behavior, but keeping it from being destroyed. because larger systems interact more easily with their environment, and every interaction carries away information that can lead to decoherence. So scientists must build extremely controlled environments where molecules are isolated from air particles, temperature fluctuations, and stray radiation in order to prevent the quantum state from breaking apart too quickly to observe interference patterns. As experiments continue to scale up in size and complexity, the next major step in exploring quantum behavior comes from the development of quantum computers, which are not just theoretical devices, but real physical systems that rely directly on quantum principles such as superposition and interference to perform calculations. And the basic building block of these systems is something called a qubit, which behaves very differently from a classical bit used in normal computers. A classical bit can only exist in one of two states at any time, usually represented as 0 or 1. But a qubit can exist in a superposition of both states simultaneously, meaning that before measurement it is described by a wave function that includes both possibilities at once, and this allows quantum computers to process information in a fundamentally different way compared to classical machines, because multiple computational paths can be explored simultaneously within the same quantum system. The important point is that this superposition is not just a mathematical trick used to simulate uncertainty, but a real physical state of the system that can be manipulated and controlled in experiments. And scientists can design sequences of operations that guide how the wave function evolves over time, so that different parts of the superposition interfere with each other in ways that produce useful computational results when the system is finally measured. However, maintaining this delicate state is extremely difficult because qubits are highly sensitive to their environment, and even tiny interactions with surrounding particles can cause decoherence, which destroys the coherent superposition and turns the quantum system into a classical one, where interference is no longer possible. And this is why a large part of quantum computing research is focused on reducing noise and isolating qubits so that they can remain in superposition long enough to perform meaningful calculations. In this context, decoherence is not just a theoretical concept, but a practical engineering problem that determines whether a quantum computer can function at all, because every unwanted interaction between the system and its environment effectively leaks information about the state of the qubits. And once that information spreads into the environment, the system behaves as if it has selected a single outcome, even though the underlying wave function continues to evolve according to quantum rules. This practical struggle with decoherence gives direct experimental support to the idea that quantum systems naturally tend to branch into separate outcomes when they interact with their surroundings, because every loss of coherence corresponds to the system becoming effectively split into independent parts that no longer interfere, which mirrors the same branching behavior described in theoretical interpretations of quantum mechanics, where multiple outcomes evolve separately after measurement-like interactions. Another important area of experimental evidence comes from photon interference experiments conducted over long distances, where scientists send individual photons through carefully controlled optical systems that preserve their quantum state as they travel. And these experiments show that photons can maintain coherence over surprisingly large distances, as long as environmental interference is minimized, allowing them to interfere with themselves in ways that confirm their wave-like behavior. In these setups, maintaining coherence is extremely challenging because photons are constantly at risk of interacting with stray particles or imperfections in the optical medium, and each interaction can destroy the delicate phase relationships required for interference. So researchers use vacuum systems, cryogenic environments, and highly precise optical components to ensure that the photons remain isolated enough to preserve their quantum behavior throughout the experiment. When these conditions are met, photons continue to behave as if they are described by a wave function that extends across multiple possible paths, and when the paths are recombined, interference patterns appear that match the predictions of quantum mechanics, showing once again that quantum behavior is not limited to microscopic scales, but can persist in systems that are carefully protected from environmental disturbance. These experiments also help reinforce an important point about measurement, which is that interference disappears not because the system becomes physically classical on its own, but because interactions with the environment effectively record information about the system. And once that information exists in any accessible form, the different components of the wave function stop interfering with each other and begin to behave as separate outcomes. Across all of these experimental domains, from large molecular interference to quantum computing systems and long-distance photon experiments, one pattern remains consistent, which is that quantum behavior depends not on the size of the system, but on how isolated it is from its environment. Because as long as coherence is preserved, the system behaves according to quantum rules. And as soon as decoherence occurs, the system begins to behave in a classical way, even though the underlying quantum description remains unchanged. This leads to one of the most important observations in modern physics, which is that no experiment has ever directly confirmed a physical collapse of the wave function. Because in every case where quantum systems are measured, the results can be explained by unitary evolution combined with decoherence. And while measurements always produce definite outcomes, there is no experimental evidence that shows a distinct physical process where the wave function suddenly stops evolving and reduces to a single state. Instead, what experiments consistently show is that quantum systems remain governed by the same equations at all times, and the appearance of single outcomes can be explained through the interaction between the system and the environment, which spreads information and prevents interference, rather than through any observed collapse mechanism that would require modifying or breaking the standard mathematical framework of quantum mechanics. As experimental techniques continue to improve, scientists are able to probe increasingly complex systems while still observing quantum effects under controlled conditions, which gradually strengthens the evidence that quantum mechanics applies universally, even though the classical world we experience appears stable and definite due to the overwhelming effects of decoherence at large scales. What makes this body of evidence especially important is that it does not rely on interpretation alone, because each experiment provides measurable results that match quantum predictions with high accuracy, and while different interpretations of quantum mechanics may disagree on what these results mean in terms of reality, they all agree on the experimental outcomes, which means that the growing ability to observe quantum behavior in larger systems continues to reinforce the same underlying mathematical structure that has been successful since the early development of quantum theory. Why you don't notice branching. Quantum processes are not limited to special situations because they are constantly happening everywhere in the real world at all times. And the reason we do not notice them is not because they stop existing, but because they disappear from view almost instantly due to how quickly interactions with the environment destroy the conditions needed to observe them directly. The key idea behind this is something called decoherence timescale, which refers to how fast a quantum system loses its ability to show interference or remain in a coherent superposition when it interacts with its surroundings, and for systems that are large enough to be considered macroscopic in everyday life. This timescale is not slow or gradual, but extremely short, often measured in femtoseconds, which is 1/4,000,000th of a second, meaning that the transition from quantum behavior to classical appearance happens so quickly that it is impossible for human sensors or normal instruments to directly follow it in real time. To understand what this means, imagine a system made of many particles, such as a small object that we can see and touch, because at the microscopic level, that object is constantly interacting with air molecules, photons of light, vibrations in the surrounding material, and countless other environmental factors. And each of these interactions carries away information about the state of the system, which means that even if the system starts in a delicate quantum superposition, Those interactions immediately begin to spread that information into the environment in a way that prevents the different possibilities from remaining connected. This spreading of information is what causes decoherence, and it happens so rapidly for macroscopic systems that the quantum superposition effectively breaks apart almost instantly after it forms, not because the system stops following quantum rules, but because the environment becomes entangled with the system in such a complex way that the different parts of the wave function no longer overlap or interfere with each other, which gives the appearance of a single, definite outcome even though the full quantum description still contains all possibilities. The environment plays a central role in this process because it is not just a passive background, but an active system made of an enormous number of particles that are constantly interacting with everything around them. And every time a quantum system interacts with even a single particle in the environment, that interaction can carry away a small amount of information about the system's state. And when this happens repeatedly across trillions of interactions, the information becomes so widely distributed that it cannot be reconstructed or reversed in any practical way. This is why physicists often describe the environment as a kind of continuous measurement process, not in the sense of conscious observation, but in the sense that every interaction between a system and its surroundings acts like a recording event that captures some information about the system's state. And once that information is recorded in the environment, it effectively selects a stable outcome from the perspective of each local branch, even though the underlying wave function continues to evolve without interruption. In this view, there is no sharp boundary between a system being unmeasured and measured, because measurement is not a single moment, but a continuous process that happens whenever information about a system spreads into its surroundings. And since no system is ever completely isolated, this means that measurement-like interactions are happening constantly at all scales, which leads to the rapid emergence of classical behavior from underlying quantum rules, without needing to introduce any special collapse mechanism. The speed of this process is what makes macroscopic quantum effects so difficult to observe, because while small isolated systems like single photons or electrons can maintain coherence long enough for interference patterns to appear, larger systems lose coherence almost immediately due to the sheer number of environmental interactions they experience. And this difference in timescale explains why quantum behavior is visible in carefully controlled experiments, but not in everyday objects. When decoherence occurs, the different parts of the wave function that correspond to different possible outcomes stop interfering with each other, and instead of remaining part of a single coherent structure that can recombine, they evolve into separate components that behave independently. And this separation is what physicists refer to when they talk about branching, because each component of the wave function effectively becomes its own self-contained history that no longer interacts with the others. However, an important point is that these branches do not disappear or vanish, because the full wave function still contains all of them, and the underlying equations continue to evolve them in a smooth and continuous way. But the reason we do not observe communication between branches is because the quantum states associated with different outcomes become orthogonal, which means they no longer overlap in a way that allows interference or information exchange between them. Orthogonality in quantum mechanics is a mathematical way of describing complete separation between states, where two states are considered orthogonal if their inner product is zero. And when this happens, it becomes impossible for one state to influence or reveal information about the other through any physical measurement, which means that once branches become orthogonal due to decoherence, they effectively become inaccessible to each other within the rules of quantum physics. This is why information leakage plays such a critical role in understanding why branches do not communicate, because once information about a quantum system spreads into the environment, it becomes distributed across so many particles and degrees of freedom that no single observer or device can recover the full quantum state. And this loss of recoverability is what prevents the different branches from ever recombining in any observable way. Even though, in principle, the total wave function of the universe still contains all information about all branches, in practice the information is spread so widely that it becomes physically impossible to reverse the process, because doing so would require controlling every particle that has interacted with the system since the branching occurred, including all surrounding environmental particles, which is far beyond any realistic physical capability. This irreversibility is not due to a failure of the underlying equations, because the Schrödinger equation itself remains fully reversible in principle. But in practice, the complexity of environmental interactions creates an effective one-way flow of information that makes decoherence behave like an irreversible process at macroscopic scales, even though at the fundamental level nothing is actually being destroyed or removed from the wave function. As a result, each branch evolves as if it is the only one that exists from the perspective of observers within that branch, because all information that could connect it to other branches has been lost into the environment in a way that prevents recombination. And this is why everyday reality appears stable and definite, even though the underlying quantum description allows for multiple outcomes to exist simultaneously in different parts of the wave function. The key reason branching is not visible in daily life is therefore not because quantum mechanics stops working at large scales, but because decoherence happens so quickly for macroscopic systems that any superposition involving large objects is immediately broken into separate orthogonal states before it can be observed directly, which creates the appearance of a single classical outcome emerging from what is actually a much larger quantum structure evolving underneath. The physical self inside quantum branching. The moment quantum branching is applied to systems that are not just particles in a lab, but complex living structures, the focus shifts from abstract experiments to something much more grounded in physical reality. Because a human being is not outside the laws of physics, but fully built from the same particles and fields that follow quantum rules at every level. And this means that the same processes that create branching in simple experiments must also apply to the physical systems that make up the brain and body, even if the effects are not visible in everyday experience due to how quickly decoherence removes any direct trace of quantum overlap between different outcomes. The continuity of brain states is not a single fixed object staying unchanged through time, but a constantly updating chain of physical configurations where each moment of brain activity depends on the exact state of the previous moment. And those configurations are defined by electrical signals, chemical activity, and particle interactions inside the brain, all of which evolve according to physical laws without any part of the system standing outside those laws, which means identity in physical terms is tied to this ongoing sequence rather than to a single stable structure. When this is placed inside quantum mechanics, each transition between brain states is influenced at the smallest scale by microscopic physical events, many of which involve quantum uncertainty. And while most of these events average out into stable biological behavior at the larger scale, some of them become part of processes where tiny differences can affect whether certain neurons fire or not. And once that happens, the difference can spread through connected neural networks and become amplified into different macroscopic brain states that cannot be merged again once decoherence has taken place. A divergence point is what happens when one of these small microscopic differences becomes large enough to affect the overall evolution of the system, and this does not require anything dramatic at the start, because it can begin with a single quantum-level event, such as a slight timing difference in ion movement or a small variation in a molecular interaction. But because the brain is a highly interconnected system, that small variation can change patterns of neural firing and eventually lead to different physical outcomes in behavior or internal processing. Once this divergence occurs, decoherence ensures that the different outcomes stop interfering with each other almost immediately, because the environment continuously interacts with the system and spreads information about each outcome into surrounding particles, which means the wave function describing the system separates into distinct components that no longer overlap in a way that allows them to influence each other. And from that point forward, each component evolves independently under the same physical laws, but without any further connection to the others. Each of these separated components forms what can be described as a competing future trajectory, where every branch contains a complete and consistent version of the system evolving forward in time based on the specific microscopic events that occurred earlier in that branch. And since these events differ between branches, the later evolution of each branch also differs, leading to different sequences of physical states that all remain internally consistent within their own structure. From the perspective of an observer inside any one branch, only a single trajectory is ever experienced, because all information available within that branch supports one continuous history, where events appear fixed and definite, while the alternative trajectories are not accessible because the information that could connect them has been spread into the environment in a way that prevents recombination or interference, which makes each branch effectively isolated, even though they are still part of the same overall quantum system. The key point is that these trajectories are not created by any central decision process in physics, because quantum mechanics does not include any rule that selects one outcome over another. And instead, all outcomes exist in the wave function before decoherence separates them. And once separation occurs, each outcome continues independently without requiring any additional mechanism to determine which one is real, since all are treated equally by the underlying equations. This is also why physics does not contain a central observer that decides what becomes real, because the equations of quantum mechanics apply equally to all physical systems, whether they are particles, measuring devices, or complex biological structures, and observation is not a special process that changes the rules, but simply an interaction between systems that leads to information being distributed through the environment. In this framework, there is no single privileged outcome selected by nature when a measurement occurs, because the mathematics does not include any collapse rule that removes alternatives, and instead each possible outcome becomes part of a separate branch once decoherence takes place, and each branch evolves independently with its own consistent history, including versions of observers who experience only that branch without any awareness of the others. This removes the need to define a boundary between observed and unobserved systems, because all systems are treated under the same physical laws, and the difference between quantum and classical behavior arises not from different rules, but from how quickly decoherence spreads information into the environment, which determines whether interference between different outcomes can still occur or has already been destroyed. The universe as a continuous branching system. When quantum mechanics is taken seriously as a universal rule that applies not just to small particles in controlled labs, but to everything in existence, the scale of what it describes expands far beyond simple experiments, because the same physical laws that govern electrons and photons also govern stars, planets, gas clouds, radiation, and every form of matter and energy in the universe. And this means that quantum events are not rare or isolated, but constantly happening everywhere at every moment across cosmic history. At the smallest scale, quantum events involve things like particle interactions, energy exchanges, and decay processes. But when these same rules are applied across large systems that contain enormous numbers of particles, the number of quantum events happening at any given time becomes almost impossible to count, because every region of space filled with matter and radiation is constantly experiencing microscopic interactions that follow quantum probabilities rather than fixed deterministic paths. One of the clearest examples of quantum events happening at a large scale comes from star formation, where huge clouds of gas and dust in space slowly collapse under gravity. But this collapse is not a simple, smooth process, because inside those clouds there are constant quantum-level interactions between particles, including collisions, emissions of radiation, and energy exchanges that are governed by probabilistic quantum rules. And these small-scale events influence how matter distributes itself over time as the cloud evolves. As the cloud becomes denser, radiation plays a major role in shaping its structure, because photons are constantly being emitted and absorbed by particles, and each interaction follows quantum rules that determine when and how energy is exchanged. And even though the overall behavior of the cloud looks continuous on a large scale, at the microscopic level, it is built from countless quantum events that contribute to the final structure of the forming star, and different possible microscopic outcomes are always present in the full quantum description of the process. Another important example comes from radioactive decay, where unstable particles inside atoms change into other particles over time, and this process is not triggered by any external force or predictable mechanical cause, but instead follows a quantum probability that determines when a decay event will occur, meaning that each atom has a range of possible outcomes over time, and the exact moment of decay is not fixed in advance, but is described by a probability distribution that reflects the underlying quantum rules governing the system. In large systems containing many radioactive atoms, this leads to a continuous flow of decay events occurring at random times according to quantum probabilities, and each of these events represents a quantum branching point where different outcomes are possible in principle before decoherence takes place, because the decay either happens or does not happen at a given moment. And once it happens, the resulting particles interact with their surroundings in ways that spread information into the environment and separate the resulting outcomes into non-interacting histories. Particle interactions throughout the universe also contribute to this constant flow of quantum events, because particles are never truly isolated in empty space, and even in regions that appear almost empty, there are still interactions with background radiation, virtual particles, and quantum fields that fluctuate continuously, and each interaction follows quantum rules that allow for multiple possible outcomes before one becomes effectively realized through decoherence and environmental interaction. When these processes are viewed together, star formation, radiation exchange, particle decay, and all other quantum interactions are not separate, isolated events, but part of a continuous fabric of quantum activity that fills the universe at every scale. And this means that the number of quantum events happening at any moment is so large that it becomes more accurate to think of the universe as a constantly active quantum system rather than a collection of separate classical objects moving through space. If every quantum event allows for multiple possible outcomes before decoherence separates them, then the full structure of the universe under quantum mechanics can be described as a continuously expanding branching system, where each event adds new structure to an already existing network of possible histories, and this network grows over time as more quantum interactions take place across all regions of space. In this view, the universe is not following a single fixed timeline where one outcome is selected at each event, but instead evolves into a branching tree where each quantum event produces a set of possible outcomes that become separated into different parts of the wave function once decoherence spreads information into the environment, and each of these parts then continues to evolve independently according to the same physical laws, without interacting with the others. This branching process is not something that happens in discrete steps that can be easily counted, because quantum events occur continuously and overlap across space and time, which means that the branching structure is constantly being reshaped and expanded as new interactions occur, and older branches continue to evolve into increasingly complex histories that reflect the accumulated results of many earlier quantum events. Over long periods of time, this leads to an extremely large and complex structure of possible histories, where each branch represents a consistent sequence of events that could have occurred based on different outcomes of quantum processes. And although all of these branches exist within the same underlying wave function, they do not interact with each other once decoherence has separated them, which makes each branch behave like an independent classical world from the perspective of observers within it. The important point is that this branching tree is not a literal physical tree growing in space, but a way of describing how the mathematical structure of the wave function evolves when it is influenced by constant environmental interactions, and each new quantum event adds further separation between possible outcomes, making the overall structure more complex over time, without requiring any external selection mechanism or collapse process. Once decoherence has occurred and branches have formed, one of the most important physical results is that these branches do not interact with each other in any observable way, because the quantum states that represent different outcomes become orthogonal, meaning they no longer overlap in the mathematical sense required for interference or information exchange. And this separation is not temporary, but becomes effectively permanent under normal physical conditions. This lack of interaction is not due to any hidden barrier or force preventing communication between branches, but arises naturally from the way quantum information spreads into the environment. Because once information about a particular outcome is distributed across many particles in the environment, it becomes impossible to reconstruct or reverse that information in a way that would allow the different branches to recombine and interfere again. Even though the full wave function still contains all branches in a single mathematical description, the practical separation between them means that each branch evolves independently, and no observer within one branch can access information from another branch because all traces of connection have been dispersed into environmental degrees of freedom that are far too complex to control or reverse in any realistic physical scenario. This is why cross-branch interaction does not occur in practice, because once decoherence has taken place, the conditions required for interference no longer exist. And even though the underlying equations of quantum mechanics remain reversible in principle, the sheer complexity of environmental interactions ensures that branches remain isolated from each other for all practical purposes. As a result, each branch behaves like a self-contained version of reality, where events follow consistent physical laws and produce stable outcomes that appear classical to observers within that branch, while the other branches continue evolving separately without any influence or awareness of each other, even though they all remain part of the same underlying quantum structure that describes the entire universe. The breakdown of single outcomes in quantum reality. When quantum mechanics is applied to everything in the universe without making exceptions for size or complexity, one of the most important results is that the idea of a single fixed outcome for every event starts to break down at the fundamental level, because classical physics assumes that every process has one definite result that can be predicted if all starting conditions are known, while quantum physics replaces this with a structure where multiple outcomes exist in the mathematical description before interaction with the environment separates them into independent histories that no longer affect each other. In classical thinking, the universe is expected to behave like a single, continuous chain of causes and effects, where every event leads to one specific next event. And if enough information were available, the entire future could in principle be predicted with complete accuracy. But quantum mechanics removes this certainty at the smaller scale, because even when a system is fully described, the outcome of certain events is not fixed in advance, but is instead described by a range of possibilities, governed by probabilities that only become separated into distinct results after decoherence spreads the effects into the environment. The loss of single outcome determinism begins at the level of individual quantum events, where particles and systems do not follow one fixed path or produce one guaranteed result, but instead evolve through a mathematical structure that contains all possible outcomes allowed by the physical laws, and this structure does not collapse into a single outcome through any known physical process, but continues evolving as a whole while interactions with the environment determine how different parts of the system become separated from each other. In practical terms, this means that when a quantum event occurs, such as a particle interaction or a decay process, the system does not move from a single initial state to a single final state in a classical sense, but instead moves into a situation where multiple outcomes exist simultaneously within the wave function. And these outcomes are not abstract possibilities in the usual sense, but physical components of the quantum description that evolve according to the same equations before decoherence separates them. Classical physics assumes that randomness is only due to missing information, meaning that if everything were known precisely, the outcome would be predictable. But quantum physics shows that even with complete information about the wave function, only a range of possible outcomes can be described, and there is no additional hidden mechanism within standard physics that selects one outcome over another, which removes the idea of strict single outcome determinism at the fundamental level. As these quantum events accumulate across time, the loss of single outcome determinism becomes more significant because each event adds new layers of possible outcomes to the evolving structure of the wave function. And although decoherence ensures that these outcomes do not remain connected in a way that allows interference, they still exist within the full physical description, which means that the universe is not following one fixed path, but instead contains a continuously expanding set of possible histories that develop in parallel without interacting. This does not mean that everyday life becomes unpredictable in a chaotic sense, because at large scales, the effects of quantum uncertainty average out into stable patterns that appear deterministic. But at the microscopic level, the absence of a single guaranteed outcome remains fundamental, and it is only through environmental interaction and decoherence that stable classical behavior emerges from this deeper structure. When quantum branching is applied to complex physical systems like the brain, identity is not treated as a philosophical concept, but as a physical process based on the continuity of brain states over time, where each state is defined by the exact configuration of particles, electrical signals, and chemical activity in the brain at a given moment. And this sequence of states forms a continuous physical chain governed by the laws of physics without requiring any additional non-physical elements. In this framework, identity is tied to physical continuity rather than any single unchanging structure, which means that what is experienced as a stable self is actually a rapidly updating system where each moment depends on the previous one through continuous physical interactions. And since all of these interactions follow quantum rules at the smallest scale, the brain is also subject to the same branching structure that applies to all quantum systems when multiple outcomes become possible before decoherence separates them. When microscopic quantum events occur inside or around the brain, such as small variations in molecular interactions or timing differences in neural processes, these events can influence whether certain neurons fire or remain inactive. And because the brain is highly sensitive to small changes, these microscopic differences can be amplified into larger differences in neural activity, which then lead to different physical brain states that evolve separately once decoherence spreads information into the environment. This process leads to what can be described as identity fragmentation in a physical sense, meaning that when a quantum event produces multiple possible outcomes that influence brain activity, each outcome becomes part of a separate branch of the wave function where a version of the brain continues to evolve according to that specific outcome. And these branches do not interact after decoherence, which means each version of the brain develops independently as part of its own consistent physical history. It is important to understand that this is not fragmentation in space or duplication of physical bodies in a classical sense, because nothing is being copied or split into separate objects in the physical world. Instead, what changes is the structure of the quantum description, where different outcomes of microscopic events lead to different non-interacting evolutions of the same underlying system within the full wave function. Each resulting branch contains a complete and consistent version of the brain and body evolving forward in time, shaped by the specific sequence of quantum events that occurred in that branch. And because decoherence ensures that these branches no longer interfere, each version behaves as if it is the only existing outcome from the perspective of physical processes inside that branch, even though other branches exist within the full quantum description. As quantum events continue to occur throughout the brain and environment, the possible outcomes of these events become distributed across different branches of the wave function. And this distribution is not directed by any central mechanism, but arises naturally from the probabilistic structure of quantum mechanics, where each outcome has a certain weight, determined by the wave function before decoherence separates the resulting states into independent histories. This leads to a situation where measurement outcomes are not concentrated into a single future path at the fundamental level, but are instead spread across multiple branches, each containing a version of the system that experiences a specific outcome. And once decoherence has taken place, these versions do not interact or exchange information, because the quantum states that define them have become orthogonal and no longer overlap in a way that allows interference or communication. From a physical standpoint, this means that the result of any quantum event is not a single outcome selected from a set of possibilities, but a set of outcomes that all exist within the full wave function and evolve independently once separated, which creates a structure where the effects of quantum randomness are not concentrated into one path, but are instead distributed across many non-interacting branches. In systems that involve observers, including biological systems like the brain, this distribution means that different versions of the same system can experience different outcomes of the same quantum events, and each version continues its evolution within its own branch, where all physical processes remain consistent and stable, and where the history of events appears continuous, because all relevant information within that branch supports a single coherent sequence of states. The key point in this framework is that there is no single physical process that selects one outcome as the only real one, because quantum mechanics does not include any mechanism for collapsing the wave function into a single state, and instead all outcomes remain part of the full quantum description, while decoherence ensures that they do not interact after separation, which leads to a structure where probabilistic outcomes are not eliminated but distributed across different branches of reality. This distribution is continuous over time because quantum events occur constantly at all scales, meaning that the branching structure is always expanding as new outcomes are generated and separated by environmental interactions. And although each individual branch remains stable and internally consistent, the full structure contains a far larger set of possible histories that evolve in parallel without ever recombining once decoherence has taken effect, where quantum reality still stands unresolved. At the center of quantum theory, there are several major interpretations that try to explain the same experimental results in different ways, and the most widely known is the Copenhagen interpretation, which treats the wave function as a tool for predicting probabilities and assumes that measurement produces a single outcome when the system interacts with an observer or measuring device, even though it does not clearly define what physically counts as a measurement or why that transition should occur. Another major approach is the many worlds interpretation, which removes the idea of collapse entirely and treats the wave function as always evolving under the Schrödinger equation, where every possible outcome of a quantum event exists in the full mathematical structure and becomes separated through decoherence into non-interacting branches that each contain a consistent version of reality, including observers who only experience one branch. There are also objective collapse theories, which modify quantum mechanics by adding a physical mechanism that forces wave functions to collapse into a single outcome when systems become large or complex enough. And these theories attempt to explain why we never observe macroscopic superpositions, but they require additional rules beyond standard quantum equations and have not yet been confirmed by experimental evidence. All of these interpretations agree on the same experimental results, meaning they all predict the same outcomes for every test performed so far. But they disagree on what those results mean in terms of underlying reality, which is why the debate remains open even after decades of highly precise quantum experiments. One of the most important points in modern quantum physics is that no experiment has yet been able to clearly distinguish between these interpretations, because all current observations can be explained by the same mathematical framework of quantum mechanics without requiring a unique collapse process or a specific branching structure to be directly observed. This means that whether one believes in wave function collapse, many parallel branches, or an as yet unknown modification of quantum theory, the actual predictions for measurable outcomes remain identical in all tested cases, which makes interpretation a question about the meaning of the theory rather than a question about experimental disagreement. Because of this, quantum physics remains extremely successful as a predictive tool, while still leaving open the question of what is physically happening behind the mathematical structure, since all interpretations produce the same results when applied to laboratory experiments, particle physics, quantum optics, and all other tested domains. The reason this ambiguity persists is closely connected to the limits of measurement itself. Because once a quantum system interacts with its environment, decoherence spreads information about its state across an enormous number of particles, and this process hides the underlying quantum structure from direct observation by preventing interference between different parts of the wave function. As a result, the deeper structure of quantum states becomes inaccessible in practice, even though it continues to exist in the mathematical description, because recovering that structure would require reversing every interaction that has occurred since decoherence began, including interactions with air molecules, photons, and surrounding matter, which is physically impossible for macroscopic systems. This limitation means that experiments can only observe the outcomes that remain stable after decoherence, not the full underlying evolution of all possible outcomes before they separate. And this creates a fundamental boundary between what can be measured directly and what exists only in the theoretical framework of quantum mechanics. Despite these limits, research continues to push the boundaries of what can be tested, especially in systems that try to maintain quantum coherence at increasingly large scales, because one of the main goals of modern physics is to see how far quantum behavior can extend before environmental effects become too strong to control. One major direction involves macroscopic quantum coherence tests, where scientists attempt to create and maintain superposition states in larger and more complex systems than ever before, including mechanical oscillators, large molecules, and hybrid systems that combine different physical platforms, all designed to test how decoherence behaves as systems grow in size and complexity. Another important area is quantum computing, where improved performance and stability of qubits serve as indirect tests of how well quantum coherence can be preserved under controlled conditions, since the ability of a quantum computer to function depends directly on maintaining superposition and preventing unwanted decoherence, making it a practical way to explore the limits of quantum behavior in engineered systems. These experiments do not directly confirm or reject interpretations like many worlds or collapse theories, but they do refine our understanding of decoherence, scaling, and the transition between quantum and classical behavior, which indirectly shapes how each interpretation must be applied to real physical systems. Quantum mechanics is one of the most experimentally confirmed theories in all of physics, with predictions that match observed results across an extremely wide range of systems, from single particles to complex molecular structures and engineered quantum devices. And its mathematical framework based on wave function evolution remains consistent across all tested conditions, without any observed breakdown. The evolution of the wave function under the Schrödinger equation is mathematically consistent and has never been shown to fail in any controlled experiment, which means the core structure of quantum mechanics is extremely stable as a description of physical reality, even though its interpretation remains open to different viewpoints. The measurement problem still remains unresolved at the interpretational level, because while experiments clearly show definite outcomes, there is no single universally accepted explanation within physics that describes exactly how or why those outcomes appear as single events when the underlying equations allow multiple possibilities to exist simultaneously before decoherence. The many worlds interpretation is a valid interpretation of quantum mechanics in the sense that it is fully consistent with the equations and experimental results, but it is not a directly confirmed fact of nature because no experiment has yet been able to isolate or observe separate branches of the wave function, even though the mathematical structure allows such a description. The idea of infinite U's is therefore not an observed physical phenomenon, but a consequence that arises within one specific interpretation of quantum mechanics when applied universally to all systems, combined with the role of decoherence in separating outcomes into non-interacting histories. And it remains a theoretical extension of the formalism rather than an experimentally verified feature of reality. When everything is traced back to the simplest quantum event, such as a single photon hitting a beam splitter and producing multiple possible paths in the wave function, the same structure appears again at the most basic level, where quantum mechanics allows more than one outcome before decoherence separates them into distinct histories that no longer interfere. That simple experiment becomes the foundation for everything that follows in the larger description of quantum reality, because every complex system, including macroscopic objects and biological systems, is ultimately built from the same type of quantum events, and each of those events follows the same rules of superposition, evolution, and decoherence. From this perspective, physics does not describe a single-track storyline that unfolds in one fixed direction, but instead describes a structure of outcomes governed by mathematical laws that allow multiple possibilities to exist within the same framework before environmental interactions separate them into independent histories.